welcome to the course Advanced Reaction Engineering. So, today we will continue the from our last lecture. So, that is steady state non isothermal reactor designs. So, today basically we will discuss about the reactions with heat exchange, means when there is a reactions inside of a reactor. So, then we either may supply heat if it is exothermic reactions, heat generation should be there inside of the reactor. So, then we have to take out the heat from the reactors with the help of some heat transfer fluids or mediums that will flow or circulate outside of the reactor to make it isothermal temperatures or temperature constant, or maybe temperatures depending upon that, means the way we are flowing or supplying the coolant, either it is co-current, counter current, or from the reactors throughout by maintaining constant coolant temperature. So, that depends, means here let us say this is the reactions. I said reactions may be two types, that is the one is the exothermic reactions, another one is the endothermic reactions. If exothermic heat generation should be there, then we have to supply the coolant to decrease the temperature or down the temperatures. If it is endothermic reactions, temperature would be fall or down. So, when reactions will conduct inside of the reactor, so then we have to supply the heat to maintain isothermal temperature for the reacting fluids. Okay. And heat transfer fluid or flow medium with the directions is also different. So, it may be co-current and counter current flow, how that is. So, we will discuss. So, let us say this is our reactor. So, here is a reactor. So, here is reactant and feed that is passing from the left hand side to the right hand side. This is the reacting space where reactions will take place or reactions will occurred here. So, if the reactions is let us say exothermic reactions, heat generation should be there, reacting fluid temperature will increase. So, that way product mixtures will come out at this concentration molar flow rates of component A, and this is the exit temperatures. Similarly, the coolants that is heat transfer medium or fluids that we may pass this way, means counter current directions. This is the counter current flow, it would in these sides and leave these sides. So, here also the fluid heat transfer fluid entering these sides and leaving left side. So, this flow patterns is counter current directions, means heat transfer fluids here temperature would be entering temperature would be lower, here exit temperature of the heat transfer medium or fluid temperature would be higher. Here reactant at what temperature we are feeding, that is the T0, and once reactions will start if it is exothermic. So, here high temperature reacting mixture temperature will gradually increase, but at different temperature it would leave from the reactors. So, now it may be these flow directions, flow patterns, it may be co-current, same directions, means reacting fluid is passing from left to right, and coolant also we may pass from left to right, okay, or maybe reverse directions. If it is same directions, it is called co-current flow, or if it is opposite directions, means reacting medium that is flowing from the reactor and outside of the reactor coolant is flowing from right to left, then it is called counter current. So, both the way. So, we want to see the reactor temperature profiles, means inside of the reactors, means earlier one whatever we have discussed in our previous class, that was adiabatic systems, means there is no supply of heat to the systems, whether the reactions exothermic or endothermic whatever. But here the reactions is exothermic, maybe endothermic, but here we are supplying, this is the additional fluids, means heat exchange systems is there, heat exchanger is there. Okay. So, heat we can supply heat, or maybe we can take out heat from the system or energy we can take out. So, under that conditions the reactor temperature profiles, how that would be, reactor temperature along the length of the reactors how will vary, and here coolant or reacting means that coolant also we have to supply. If Ta is the coolant temperatures, so then along the volume of the reactor, means from this is the volume started from here 0 V equals to 0, this is V equals to V. So, along the length or along the increasing the volume, so what would be the temperature of the coolant, this is the coolant temperature, this is reacting medium temperature. So, along the volumes of the reactor or progress of the reactions, what would be the nature of that for exothermic reactions as well as endothermic reactions, co-current fluids, counter current fluids. flow of fluids, that is the heat transfer medium, that we will discuss. Okay. Now, consider a tubular reactors. We are considering a tubular reactor. This is a tubular reactors or plug flow reactors. So, here assumptions, there is some assumption, that is the no radial gradients, means heat transfer changes of the temperatures along the this is there, along the length temperature variation is there, but along the radial directions there is no variations. So, here everywhere this way temperature remain same at these points, but along these directions temperature at these locations would be different. So, no temperature gradient in the reactors, and the flux to the wall per unit volume of the reactor, that we have to consider. And here I said reactions may be exothermics or endothermics. If it is exothermic reactions, heat added to the Q positive, and if endothermic reactions, Q is the negative, that is heat added or removal from the systems. Accordingly that we have to use. And now in this particular systems, this is the inlet feed corresponding temperatures, this is exit feed and corresponding temperatures. And if we consider this is the delta V small v, delta V volume, very small volume if we consider element in the reactors. So, here this is the heat entering at this particular points and leaving from this this particular point V plus delta V, and this point is V. So, small element is delta V, within that energy balance if you want to do, and here we are considering that shaft work that is equals to 0. This is the energy balance equation, equation 1 that we have discussed. So, here shaft work we are considering 0, and but Q is there, means heat we are supplying with the help of fluid, heat transfer fluids, that is delta Q, means delta Q, that is the small amount for delta V volume, and Q would be the amount of energy for, if total volume is V. So, then that much amount of the energy would be supplied for that particular reactor through reacting fluids. Okay. So, then energy balance equations we can write this way, means this energy balance equations by eliminating Ws parts, since there is no shaft work. So, only this way you can write, and here Q equal to the energy or heat supplied, either it may be positive or negative, that depends upon whether it is exothermic or endothermic, either heat supply is required or not, or heat removal is required. So, based on that it would be either positive or negatives. Okay. So, now here U is the overall heat transfer coefficient, it is given, delta that is the heat exchange area, T is the ambient temperatures, and T is the reactor temperatures. Here small a, that is the heat exchange area per unit volume, and if delta V is the total volume. So, then the heat transfer area, so that we can find out. So, heat transfer area that equals to, if we know the diameter of that reactor, so then A, that is the heat transfer area per unit volume, so we can find out. So, we can substitute here, and small delta V that we have taken consider, that we know. If TA is the ambient temperature of the reacting fluids, at what temperature we are supplying, that if know, and reactor temperatures inside of the reactor, that reaction fluid temperature is known. So, then the amount of the heat supplied easily we can find out if you know heat transfer, overall heat transfer coefficient for that particular fluid medium, if you know, or for that particular process overall heat transfer coefficient should be known. So, then that we can supply or we can provide there, and we can do it. So, now in that equations we are substituting delta Q in equation 1 and then dividing by delta V both sides and taking limit delta V tends to 0. So, then that equations would be like this. These equations, this part we are substituting here, and then dividing by both sides, left hand and right hand side with respect to the delta V, and then we are taking limit delta V tends to 0, then this type of differential equations we can get. Okay. So, now here this part means here molar flow rate and enthalpy both are there, this part we can expand this way. Okay. And this is the left part, it is remain as it is. So, now this part d sigma dFi by dV, that we can write this way, means rate of the reactions, means this is the differential equation, design equation for a plug flow reactor. So, this is we have discussed in our at the beginning. So, when we have started. So, this is equals to rate basically. So, nu I, that is the stoichiometric coefficient, and this is a rate for component A. This way we can write for species 1, and here Fa, that is the molar flow rate, equals to concentration into volumetric flow rate. So, volumetric flow rate equals to volume by per unit times. So, if you substitute it here and differentiate dFA by dV, this way it would come, then we can write this way, then dCA by dt equals to Ra. It is coming dFA by dV, that is equals to Ra. This way you can write. Okay. So, dF here it was dFA by dV, that is equals to basically rate, okay, for ith components. So, here we can substitute this rate into enthalpy, and dHi by dV, that is equals to this. This is coming from here. This is the definition for enthalpy for a particular temperature. If you know the standard or reference temperature enthalpy, heat capacity of individual components, and reference temperature to any temperature, that is the this equation also we have discussed in our previous class also. So, if you differentiate this, then after differentiating with respect to the dV, we can get this. So, here dHi by dV, that we can substitute this in these equations. dHi by dV, that is the sigma for if the reactions there are n number of components, 2, 3, 4 components. So, that we have to sum up. So, therefore, sigma has come. So, here if we consider it is a component A, then corresponding A dHa by dV Cpa dt by dV we can substitute it here. So, then it is in terms of temperature and volumes, it would be this temperature and volume in the right hand side, that way we can substitute. So, then the equations would become like this. Okay, after substituting that two part, so we are writing these equations 3. After rearranging these equations, we can get means dt by dV, that we are putting in the left hand side and rest of the terms in the right hand side, and then equations 4 we can get. So, in the equation 4, here this is component 1, this is component 2. This component 1, that is heat generated term, it is called heat generated terms, and this part is called heat removal term or removed, means Ra into delta H Rx, means when reactions is there, heat of reactions means heat formations or heat absorbed depending upon the reactions. So, from the reacting system, means for the reactions, this part is coming, therefore, it is called heat generated. If it is exothermic, then heat generation should be there, and this is heat removal terms, that is from the coming from coolant. So, that is supplied to the outside of the reactors. So, therefore, it is overall heat transfer coefficient at heat transfer area per unit volume, and this is the temperature difference, reactor temperature and ambient temperature or fluid ambient temperatures. So, this is heat removed by the coolant or heat exchangers. So, means this way it is balanced, means the temperature inside of the reactors, means one way from the reactions heat generation should be there, and from the coolant or heat exchange medium, the heat or temperature that would be removed from the systems. By that way, that would be become a steady state and equilibrium would be there, and systems will run throughout the operations for let us say 5 hours, 10 hours, 20 hours, if we run the systems that maintain the similar pattern of temperatures along the length of the reactors. Okay. So, this is called heat generated terms, this is heat removal terms, or the equations 4 we can write this way also, dt by dV equals to heat of generations, heat removal terms by Fa naught into Cpa. So, if you know the molar feed rate of component for the reactions, heat capacity of the component A, and the amount of heat generated, amount of heat removal from the system. So, by putting this we can find out the temperature profile along the volume of the reactors. Okay. So, here in the denominator terms sigma Fi Cpi, here if molar flow rates, that we can write this way, that at the beginnings we have discussed. So, that is the exit of the reactors, the component or molar flow rate of component, that we can ith component we can write Fa naught theta I nu I x. So, theta is the ratio of the mole. So, if it is component A, it would be 1, nu I, that is the stoichiometric coefficient. So, if it is component A, it would be -1. Okay. So, depending upon that, so how much that stoichiometric coefficient are there depending upon A, B, C, D, small a, B, C, D. So, depending upon this component, stoichiometric component. So, this value either it is positive, negative, or that component number would come numerical value, and theta I that we discussed f a I by if component f a I, let us say f a by f a I, it would be for component 1 I equals to if a, then it would be 1, f a naught also. So, it would be 1. So, if component B, if b naught by f a naught, f b naught by f a naught, this way we can find out. So, we have discussed, so I am not going into details on that. So, you know it. So, now this equation force we can write this way, okay, equation 5. So, this is the left hand side parts and this is right hand side part in these equations, and in the bottom. So, what are the things are there, so we can expand this and we can write in terms of heat capacity changes or whatever. This is the energy balance equation for plug reactors. So, now if the systems is packed bed reactors, then instead of volumes it would be converted into W, dt by dW, that also we have discussed. So, here in the packed bed reactors, dW equals to rho B, that is the bulk density of the catalyst multiplied with the volumes. So, density equals to bulk density equals to mass per unit volume multiplied with the volumes. So, then mass would comes. So, this way it is packed bed reactor. So, we can substitute this dV, we can substitute this or these equations, here dV is there. So, there's this dV we can substitute, then it would become this way. So, these equations we can use, this is the energy balance equation for packed bed reactor. So, equation 6 is the design equation, similar type of equations as equation 5. This is for plug reactors and this is for packed bed reactors. So, this is the temperature profile for packed bed reactors. So, here temperature and W, this is the packed bed reactors, and plug reactors temperature and volumes. Okay. So, that would come. So, that natures we have to find out. So, differential equations we have find out. So, now heat transfer fluids means here whatever we have discussed, that is the energy balance equations, that is inside of the reactors what is happens, how the temperature is varying along the length or volume of the reactor or weight of the catalyst for packed bed reactor, that we have discussed equation 6. And this is the mole balance equations for plug reactors that we discussed at the beginning. So, for any reactors, so that we can express rate and molar flow rates and dx by dV, and here equation 6, that was 5 was dt by dV, and here dx by dV. Okay. So, now another equation, since with that reactors there was a heat exchange, means heat transfer fluid is also passing outside of the reactors to maintain the temperatures, since there also would be a temperature changes along the length of the reactor. So, here let us say this inlet temperature is 30 degrees centigrades, the coolant we are entering. So, when it would move this way, its temperature may not be 30, it may be 50 degrees centigrades. So, here temperature we are getting 50 or here entering 30 degrees centigrade, since the reaction is exothermic, heat would be supplied to the coolant. So, then individual point also coolant temperature also, this TA also will vary along the length, means this TA, this is the coolant inlet temperatures, let us say coolant is entering TA naught, for TA naught, let us say these temperatures. So, here it is 50 degrees centigrade, initially it was 30 degrees centigrade. So, at this particular temperatures it may be 32, 35, 40, like that it is reached to the 50. So, this is the temperature profile for this particular systems when heat exchange is there, and for that the energy balance means differential equations equals to dTA by dV equals to UA minus TA. T is the reacting fluid temperature, T is the coolant temperatures, and mc that is the mass rate of coolant that is flowing, and cpc that is the heat capacity of the coolant. If you know at what rate the coolant is supplying and its heat capacity of that coolant, it has a property heat capacity. So, these are the component we know, overall heat transfer coefficient we know, and heat transfer area per unit area for that particular systems we have to know, we have to put it here, and then Ta that is the temperature, inlet temperature of the coolant that we know or that is known from the beginning, that is specified. This T will vary, means that is the reactor temperature, means when the reactions will take place inside of the reactors. So, this T would vary from along the length of the reactor, since inside of the reactors either it is exothermic or endothermic, it is not fixed. So, thence it would vary. So, thence this part would vary. So, thence along that what would be the temperature profile, that we can find out, and this equation for co-current and this equation for counter current, both are the same, but here this is Ta minus Ta and here co-current T minus Ta. So, now we have equations 5, 7 and 8. Equation 5 is there, that is the energy balance equations for plug flow reactors. Next is the 7, equation 7, that is the mole balance equations. So, mole balance equations, energy balance equations for that reactors reacting systems, and this equation 8 A or B either one, depending upon that whether it is co-current or counter current. So, these 3 equations we have to solve by using ordinary differential equation for plug flow reactors. So, then we can get X versus V, temperature V and Ta versus V. So, this is that means X means reaction conversions along the length, reaction temperatures along the volumes, and along the changes of the volumes the coolant temperature profile that we can find out. So, easily by using 3 differential equations you have to solve simultaneously, and we have to provide the known components, means reactions, a known component that we have to supply. So, then we can solve. This is for plug flow reactor. Similarly, for packed bed reactor also. So, here 5, 7 and 8 was taken, and here 6, 7 and 8 would be taken. 8 is for the coolant, either 8A or 8B whatever. So, these equations or this equation depending upon the nature of the flow patterns, either it is co-current or counter current, either one we have to choose differential equations. And for packed bed reactor this equation is there, and energy balance equations, this is energy balance equation, mole balance equations also, the equation 6, 7. Oh, not 7, this is similar like dx by dw minus Ra prime by Fa naught. These equations we have to use, not equation 7. So, this type of equation 7a, these equations we have to solve, minus Ra prime, since this is a catalyst use, this is rate basis, volume basis of rate, here per unit weight of the catalyst basis rates. So, these equations we have to use to solve for packed bed equations, and then this way we can solve. So, here these equations 8a and 8b, that is for endothermic reactions, heat would be added, and when reactions is exothermic, then co-current and counter currents, nature of the flow patterns. So, these equations either one, there are 4 equations for the coolant is there, 8a, 8b, 8c and 8d. So, these 2 are for exothermic reactions, these 2 are for endothermic reactions, and this one for co-current flow, this one is the counter current flow. Depending upon that, just sign conventions is there, minus plus. So, this minus or this minus you can see, or changes of this way we have to use. Okay. So, now exothermic or endothermic reactions, co-current or counter current flow or heat fluids, heat transfer fluids. So, now we are not considering counter current, only co-current we are taking. Okay. We are not considering counter current. See here co-current, this is the flow directions of coolant, this is the flow directions of reactants, same directions they are flowing, co-current flow. Okay. So, one example we will take and consider, and then how actually this equation 8a, 8b, 8c, 8d has come. So, that actually basically means derivations. So, for heat transfer fluids, if it is co-current, then rate of heat energy ins within this particular volume equals to rate of mass rate for the coolant, and if you know heat enthalpy of that at that particular volume. So, if you multiply and then rate of energy out at this particular points V plus delta V points. So, this is equals to this, and rate of heat added to the inner wall, this walls heat is added here, means heat transfer means reactor walls, the amount of the heat supplied, that is equals to this U A T minus T A. So, if you know there is no accumulations, means steady state. So, then this part is 0. So, now if we divided both side, left hand side and right hand side with respect to the delta V, and taking delta V limits tends to 0. So, then these equations we can write this way, and after rearranging or simplifications we can write this. This is the co-current flow. Here you can see this is the co-current flow, as that is the temperature profile or differential equation for that coolant temperatures. This is coolant, this is reacting mixture temperature. So, T is the coolant temperature. So, U A T minus T A co-current by M mass rate of the coolant kg per unit time, and heat capacity of the coolant mass rate we should know, and temperature of the coolant we know. So, then heat capacity also we should know, coolant properties. So, then we can simplify these equations. See here co-current, this is the co-current dTA by dV equals to this equations. This equation how that has been developed. So, it is discussed here. So, heating fluid co-current when it is, then now it is counter current, flow directions is different, then energy balance we have to do within volume V and V plus delta V, small delta V volume. So, within that we have to do the energy balance, and after energy balance the similarly we can get this is the differential equations for heating fluids or coolant temperatures, how they are varying with the volumes or along the length of the reactor, that is the for counter currents, just sign conventions is there for that. So, okay, co-current, and earlier one was the co-current and this one is the counter current. So, here's T minus T A was there, here T A minus T, the same things, just sign is different, means temperatures T A minus T A, T A minus T. Okay. So, now if we take one example, so means details derivations or discussions I am not doing. So, just you know means it is how it may comes by doing the energy balance. Now, if you take on examples numerical problems, so here reactions is the exothermic reactions, counter current fluid flow, heat transfer fluid flow is the counter current. So, this is the reactant left to right, and coolant flow is opposite directions. So, counter current fluid flow, and here the reactions is A is going to be, that is the reversible reactions. So, all component properties that is required to get the temperature profiles or means reactor temperature, heat transfer fluid temperatures, conversions along the volume of the reactors. So, for endothermic reactions we will discuss. So, molar flow rate is given, initial concentration is given, temperatures at these temperatures reaction rate constant is given. So, at these temperatures equilibrium rate constant is given, equilibrium constant Kc is given. This is the feed inlet temperature at which the reactant component entering, that is given, reactions gas constant is given, sigma theta I Cpi equals to this if there is some inert component is there. So, let us say in this particular reaction 10% inert is also there, inert may be, let us see if it is gas phase reactions 10% nitrogen is there with A. So, then that would come in the mole fractions, okay, or theta ith. So, that we can find out means 10% inert and rest 90% is the component A. So, then theta I is, this is the mole ratio. So, therefore, theta is this. So, Cpi, that is the heat capacity of inert component is given, heat capacity of component A, component B is given. So, then delta Cp, if both are same, then delta Cp we can put 0. So, this is 141, this is 41, then delta Cp would be 0. Activation energy for this reaction is given 65.7 kilojoule per mole, and heat of reactions for this reaction is given this. So, these are the known components are given, and with that UA is means heat transfer area per unit volumes and overall heat transfer coefficients that if we multiply, this part is given for this particular systems, and T is the ambient temperature or coolant temperature at which coolant is supplied here, inlet temperature, that is given 310 kelvins. At this particular temperature coolant is entering in the heat exchange site, okay, this sides, and it would leave at different temperature, means along this length temperature will at different point would be different, that actually we are going to find out. Okay. So, these are the component is given. So, now we have to find out these are the temperature profile conversions, this is for reactors and coolant. So, this is the coolant temperature, how with volumes how that would vary. So, these are the three components for endothermic reactions, counter current flow, fluid flow. So, we have to find out. So, known components are there. So, now we know means there is means we step by steps will start. Material balance equation is this, energy balance equation is this, that already have discussed, and these two are for reactor inside for reacting system or reactions, and this is also for counter current flow, that is the differential equations that already have discussed. So, now these three equations we have 5, 6 and 7. See, these 5, 6 and 7 equations we have to solve using ordinary differential equation solver. So, left hand side is the differential equation, right hand side what are the components are there, if known components parameters are given. So, this like this equation F A naught is given, F A naught is given. So, then F A naught easily we can put, minus R A we have to find out, minus R A means rate, how to find out for this feed temperature is given, specified specific conversions, x we have to put, heat of reactions that we know, heat of reactions that is also given, okay. Cpa also is given. So, then here T naught T0 is also given, T0 is also given. So, that is T0 is given, feed inlet temperature is given. So, almost all component is given. So, here what would be the T that we can find out at a specific conversions. So, now here this part is known from equation 1 we have find out, T1 is known, K1 is known, E is known, R is known, then K value at that T1 temperature we can find out, T temperature we can find out. Similarly, Kc value also we can find out using equation 3. This is from these equations put, T2 value is given, Kc2 is given, heat of reactions is given, R is given, then Kc at specified temperatures we know. So, now all these components in the equation 4 we can put. So, this T from here, T0 feed temperature known, X is 20% conversion, let us say, Kc is known, Ca naught is known, that is also given, Ca naught is also given. So, then small k is coming from here. So, rate is known, once rate is known we can put it here. So, then after once we solve, so then for we have taken the endothermic reactions, the reactor temperatures if we plot it would be like this, reacting fluid temperatures, and here the heat transfer fluid temperatures that would vary like this along the length or volume of the reactors. If both we plot in the same diagrams it would be like this. So, this is the coolant or heat transfer fluid temperature profile along the length or volume, and this is the reactions fluid temperatures. Certainly at this particular point it would be jump, temperature inside of the reactors will jump high and then it would be down. So, both reacting fluid temperature inside of the reactors, the reacting mixture temperature, it would vary like this. it has started from here, and coolant temperature started from here T A naught initial temperature, and this is coolant temperature would vary like this. So, in a single diagram we can plot, or either this way or this way also can put, and conversions, since the reactions was endothermic reactions along the length, the conversions will vary like this, and equilibrium conversions for this systems for this particular reactions it would follow like this. This is equilibrium conversions diagram, and this is profile for reactions actual or real reactors, the conversions varying along the volume, and this is equilibrium conversion. So, we are here close to equilibrium we have reached at this particular point. Here this is the deviation in between actual conversions and equilibrium conversions. Similarly, for this was endothermic reactions, if we consider exothermic reactions similarly, and co-current coolant flow is there. So, then heat transfer fluid temperature profiles would be this for exothermic reactions. This is the temperature profiles, means initially reactions is exothermic reactions, coolant temperature was started from here. So, then coolant temperature gradually will increase as the reactions will, since exothermic reactions heat generation should be there, as a result coolant temperature gradually will increase like this. But in endothermic reactions coolant temperature was falling this, it was started from here, and exit of the reactors it would be this. Okay. Coolant temperature is gradually downing, and in this case coolant temperature gradually will increase in case of exothermic reaction, and reactings or reactor temperature what would happens along the length it would be like this, means reacting fluid temperature it would vary like this. Both will plot in the same diagram. So, then this is reaction fluid temperatures and this is coolant temperatures. So, this way it would vary for exothermic reactions and this is for endothermic reactions. Okay. So, today is up to this. Thank you. So, we will discuss something else in our next class. Okay. Thank you.